back to Power Electronics, and this is our second part in a two-part video sequence on PWM inverters. And let's go over to the overview of what we're going to cover in this video. And in this second part video, we're going to look at the bipolar double-edged naturally sampled PWM inverter topology. The previous video, we looked at the trailing edge naturally sampled inverter. And in the double-edged, we're going to use a triangular-shaped waveform to generate our carrier. We're going to discuss the roles of the reference signal and the carrier. Again, this time for the double-edged naturally sampled inverter, it's going to be a triangular-shaped pulse. We'll qualitatively compare the trailing edge, our sawtooth pulse from the previous video, to the double-edged sampling for generated power signal through an inductive load. And we'll use the same inductive load that we used in the past video for doing that comparison. And then the second part of this video, we're going to introduce what's called the unipolar or three-level PWM inverter. And this inverter topology will also be doubly edged, meaning we're going to have a triangular-shaped waveform as our carrier signal. And then we'll qualitatively compare the differences between the unipolar PWM inverter to the bipolar inverter. Here are our references. I will provide these references in the description below. And a couple things to note. There's some really good research that is done at University of Wisconsin, which Thomas Lipo is associated with, as well as University of Minnesota. So in the Midwest, if you're planning on doing graduate work in power electronics and power converters, University of Minnesota and University of Wisconsin have outstanding graduate programs and some really good researchers there. So just a shout out to Dr. Lipo and Dr. Mohan. Here's the schematic or topology of our bipolar double-edged naturally sampled PWM inverter, and there's a lot of words in there. Let's look at them a little bit. Naturally sampled means that our reference signal is going to be sampled via analog, if you will. That's one way to think about that. Doubly edged is our carrier signal, and you'll notice on this topology we are using a triangular shaped waveform as our carrier to compare against our reference. These naturally sampled inverter topologies that I'm introducing in these video sequence is just the tip of the iceberg on converter technology. There's more topologies if we look at how we control our switching logic for our power devices proper. And oftentimes this analog circuit is replaced by an embedded controller, and allows us more flexibility in programming characteristics. If we use an embedded controller here, our reference can be placed into lookup tables, and the cost of embedded controllers has also come down. So, but if you understand these naturally sampled inverter topologies, it'll be an easy transition when you go into design and replace the control structure with something that is digital based. As we look again on our double-edged inverter, we see that M1 and M3 form a pair, and they are turned on and off at the same time. M2 and M4 also form a pair, and they get turned on and turned off at the same time. And finally, you'll notice that our M1 and M4 are complementary pairs, and they will never be on at the same time. Likewise, M2 and M3 will never be on at the same time. I adjusted the logic circuit in here, and I showed our driving circuit having both a high logic and a complemented logic on its output, just for clarity on the schematic. Here we show our reference signal, and we graphed our reference signal against our carrier signal, and the same quantities apply for this device. Recall that M sub A was equal to the maximum value of our reference divided by the maximum value of our carrier. And for this one, you can see we have a maximum value of our carrier of 1 and a maximum value of our reference at about 0.95. And so this one has an MA of 0.95. And also M sub F, which is our index of modulation for frequency, is equal to the frequency of our carrier divided by the frequency of our reference, and I label that F sub 0. Our reference signal for these examples is a 60 hertz reference, and we see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles within nine carrier cycles within one reference cycle, and so our frequency index modulation is 9 for this example. So same thing applies. As we look here, our reference will be greater than our carrier for this period of time, and therefore M1 and M3 will be switched on. And then when our reference goes higher than our carrier for this period of time, we'll see that M2 and M4 are on. This period M3 and M1 are on. And then here we go low. And in this period of time, I bring this down to the axis. Again, we have M1 and M3 on, and then finally, this period of time, M2 and M4. And so we'll switch up and down from plus VDC to minus VDC, and the width or the duty cycle of that interval will be dependent upon the relationship to the carrier to our reference signal. Same as the trailing edge, just a slightly different waveform. And here we show the waveform graphed with our carrier and reference signal. And as I said, between this period of time and this period of time, M1 and M3 are on. And then between this period of time and this period, which brings us up to plus VDC, and I have VDC normalized. And between this period, our carrier is greater than our reference, so we're below, and then between this period of time and this period of time, our reference is greater than our carrier. So again, M3 and M1 are on, which will bring us up to high VDC, and then this period of time, so on and so forth. And so you can see the duty cycle changes as we go as our reference signal goes through its cycle. Now here I've plotted in blue. The blue signal is from our trailing edge topology, and then the pinkish symbol is from our double-edged, our triangular shaped waveform. And you can see there is just a slight variation in the waveforms. It's not great nor drastic, but there's a slight one. This has a modulation index for the amplitude of 0.95. We have a carrier frequency of 10.8 kilohertz, so I believe that's 180, our value for our modulation index. And yep, MF equals 180. And we have a load of 25 ohms and 80 millihenries. Our DC voltage is 50 volts. So we're just comparing our triangular shaped wave to our sawtooth, and at a high level, there's not much difference. Where it starts to get different is if we do a spectral analysis, we're going to see some harmonics. And when we do a spectral analysis of the current through these loads, we will have one fundamental at our reference signal frequency, which is 60 hertz. And then all of the other frequency components will be centered around our carrier frequency up at 10.8 kilohertz. And the trailing edge will give us slightly different spectral around 10.8 kilohertz as compared to our triangular shaped pulse, or our double-edged pulse. Same comparison, but we've changed the amplitude index to 0.5, so we brought down the amplitude. Recall that we can control the amplitude of the current through the line between our H-bridge load by adjusting our M sub A, or the amplitude of our reference signal compared to our carrier signal. And so we brought this amplitude down for the sine wave reference down to 0.5 in the amplitude. And here now, qualitatively, not much difference. They are overlapped, and you really can't see the the trailing edge pulse. Now let's switch over, and I want to introduce a different topology. It's called a unipolar, and we're going to go with a double-edged naturally sampled inverter. However, we could go with a trailing edge on this one as well. We would just change out our carrier signal generator. We'll have 3 different possible output voltages across our load. The possible output voltages will be plus VDC, 0, and minus VDC. Whereas with the past examples, with the bipolar examples, it was either high or low. There was no in-between state. And on this example, we're going to get an in-between state. Because it is possible for M1, depending on the reference signal as it relates to our carrier, for M1 and M2 to be turned on at the same time. And when that happens, we have plus VDC here and plus VDC at this node, and therefore the voltage potential across our output is equal to 0. And it's also possible, depending on the position of our reference amplitude relative to our carrier amplitude, to have M4 and M3 on at the same time. That would then place our reference node potential on both sides of our load, creating a 0. So that case happens when we are either have our reference signal going all positive or all negative. We'll see those situations. Also notice that M1 and M4 are a complementary pair, so we cannot turn them on at the same time. Likewise, M2 and M3 form a complementary pair, and we cannot turn those on at the same time as well. And that protects from shoot-through. We don't want to destroy the devices if we would have M1 and M4 on, and our DC bus voltage would go straight to ground. So let's look at some of the waveforms. And the brown waveform is our normalized output voltage across our load. And one of the things you'll first notice with this switching topology is if our reference signal is positive, the PWM on our output will vary from 0 volts to VDC volts. And again, I have our output normalized, was 50 volts. I slightly normalized just to show it on the graphics better. And when our reference signal is negative, our output will fire between 0 and minus VDC. And the way we do that is by inverting our reference signal and comparing it. So the green line is an inversion of the reference signal. Let's go back to that topology and look where that's coming from. Right here, you can see we invert our reference signal to compare, and that's being done with this comparator down here. And on this one, we're doing the comparison on a non-inverted reference signal. So we compare our carrier to an inverted reference, and we compare our carrier to a non-inverted reference. And by doing that, we can get the different states for switching. And we see we have what's called a unipolar or 3-level inverter using that logic. Now let's compare. In this graph, we're comparing the unipolar double-edged naturally sampled PWM output. We have a modulation index for amplitude of 0.95, and we have a frequency index of 21. Our reference is a 60 hertz sine wave. And here you can clearly see the difference between our output voltage across our load for the 2 different types. The lower graph is the bipolar, where we are adjusting the output voltage by adjusting the duty cycle along the way. And the top one, you can see we are adjusting the duty cycle, but we are also going positive. So if we looked at our reference signal would look something like this. And we would have the same reference signal here. It's just a little bit trickier to see in this waveform, so on and so forth. So a qualitative comparison between the outputs of the two for similar situations. Applying those voltages to our 25 ohm and 80 millihenry inductive load, you see we get very similar current graphs through those lines. So these are the current, the top one's the current through the unipolar or three level inverter, and the bottom one is through our bipolar. So again, very similar when we look at it at a high level, fairly high index of modulation of 0.95. Now let's zoom in though and find out what the differences are. Here I've lowered the modulation index to 0.25, our peak amplitude lowers. The pink one is our unipolar signal. The blue one is our bipolar signal. And as you look on here, we have current ripple that is much greater, current ripple on the bipolar inverter output as compared to the ripple current that is on our unipolar output. And that is because our output is always switching from a minus VDC to a plus VDC. Even as we decrease our index of modulation for amplitude to 0, and if MA goes to 0, that means our current should go to 0 because the average output across the load would go to 0. We're still going to have some ripple current as it switches back and forth. Let's zoom in. And here you can see, it. I show our voltage switching. This is our voltage switching for the unipolar. And the blue one, the blue graph is our bipolar. I don't have our bipolar switching output voltage on this graph. Same load, same index. So just to zoom in on there, and you can really see that ripple current on the line for the bipolar case as compared to the unipolar case. And now let's, I think in this next one, in this next one, I set MA equal to 0. And when MA is equal to 0, our unipolar system really just stops switching altogether. And our bipolar system will switch back and forth with a duty cycle equal to 50% when we set our reference output equal to 0. You can see that here we have a very, I don't want to say it's a very high ripple current, but we have a high ripple current that is at the frequency of our carrier switching. Whereas with the unipolar case, which is the pink one underneath here, there's no ripple current on there. And that's advantageous if we want to use our inverter to control a motor. There are times when we're going to bring the motor voltage down to 0, and doing so with a unipolar PWM inverter would eliminate the ripple current through the windings. So key points from this video. We introduced the double-edged naturally sampled PWM inverter, both bipolar and unipolar topologies. That double edge was basically a triangular shaped waveform for our carrier as compared to a sawtooth waveform. The bipolar PWM inverter commutes its voltage from plus VDC to minus VDC and alters the average output via modulation of the duty cycle. The unipolar PWM inverter commutes from either 0 to plus VDC or 0 to minus VDC depending on the reference signal. So when the reference signal is negative, we're going to have the 0 to minus, and when our reference signal is positive, we're going to have the 0 to plus. And then the average output is altered via the modulation of the duty cycle as well. So there's two different aspects to that one. One of the key points on the unipolar PWM or the 3-level PWM inverter is if we set our output voltage to 0, and we do that by setting our modulation index to 0, and we do that by setting our reference amplitude to 0, we'll have basically 0 ripple current through the line or the load attached to that. However, for a bipolar inverter, we'll still have full voltage, but with a 50% duty cycle. And so we're going to see some current ripples through the line on a bipolar inverter. And so that leads to the last point and the key point. When our index of modulation for amplitude is low, then our current ripple through the load for the bipolar is constant and does not change, but for the current ripple for the unipolar PWM will decrease. So that is what I have for our PWM inverters. Again, we've just touched the iceberg, the tip of the iceberg on inverter power technology, and there's much more to study and develop as we look at how we address that control strategy. Thank you for watching.